So there are a lot of normal distributions depending on the values of mean and standard deviation. One of them is very special. It's the one with mean 0 and the standard deviation 1. Okay, as we said, given these two values, we decide a particular normal distribution. So as these two numbers are fixed to 0 and 1, there is only one normal distribution that can be called the standard normal distribution. It's the one with mean 0 and the standard deviation 1. So its curve will look like this. Standard deviation mean at 0 and the standard deviation 1. All the normal distributions can be transformed to the standard normal distribution. What does that mean? Suppose I give you a normal random variable. Let's call it x. So x describes a random event, and the probability distribution is normal, with mean mu and the standard deviation sigma. And then I can always construct another normal distribution, normal random variable, with mean 0 and the standard deviation 1. How? I simply need to get x minus mu divided by sigma. What does that mean? Previously, when I have a random variable, that means when I randomly draw a value from that distribution, how I get that value is controlled by the probability density. Okay? And now, whenever I get a value, I subtract that value, I subtract mu from that value, and then divide this value with sigma. So whenever I draw a random value, I do this transformation. If I really do that, then always I can expect my result to follow the normal distribution. Okay? So as an example, suppose previously x is within is a normal distribution with mean 10 and the standard deviation, let's say 3. Okay? Then I say z, if I define z as something like this, then z will be a normal distribution, with mean 0 and the standard deviation 1. Okay? If I randomly generate 1000 values from this normal distribution, then all those values, most of the values will be close to 10, right? Because it's the mean. And then after I do this transformation, most of the data will be close to 0. I will do some demonstrations in class. But anyway, keep this in mind. As long as we subtract the original value by mu and then divide it by sigma, we will get a standard normal distribution. And this process is called standardization. With that idea in mind, we define something similar. Consider any set of data. For any value there, we define its z-score as x minus mu divided by sigma. So what's this? This is just the formula for standardization, right? So how does this z-score be meaningful? It's that the z-score measures how far this value is from the mean. And the measurement is using the standard deviation as the unit of measurement. Okay, so I will not say this value is above mean by 2. I don't really care about whether it's by 2 or by 20. I care about how is the distance, how much time is the distance with respect to standard deviation. Okay, so for example, if z is 2, okay, if I randomly get x and if the corresponding z-score is 2, then the value, that means the value is 2 standard deviations above the mean. okay? Because I can do this calculation, and that means my value x equals mu plus 2 sigma, okay? If I have this formula, then of course I get this, and that means my value x is above mu by 2 sigma, okay? Z value may be positive or negative, and if x is smaller than mu, then the z score is negative. Okay, so now you have a lot of questions to ask. One of them is, why do we care about z score? Okay, so z score is very useful because it provides a measurement from the center that can be compared across different data sets. Okay, some data sets their values are just large, some data sets their values are just small. So it's very unfair to compare the absolute distance from each value to the mean. But if we standardize all of them into z-scores, then we somewhat is doing a meaningful comparison, no matter how these different data sets comes from. This concept will be used in the future. And also, within a single data set, z-score is also useful. Let's see the following situation. Now, let's ask this question. Suppose I get a value and it's 2 sigma away from the mean. And then I ask, do I still think this value is normal or not? Or I am asking, how likely may I get a value that is 2 sigma away from the mean? Okay, that's my question. Let's try to answer it. Let's use this story as an example. Suppose my mother sells candies in bags. My mother asked me to put candies in bags, and I should make each bag weigh 2 kilograms. Okay, so that's somehow I need to control the quality of my product. No bag should weigh more than 2.2 kilograms or less than 1.8 kilograms. That's some rules set by my mom. Unfortunately, I am not a careful person, and when I put candies into bags, I may make some errors. Suppose X is the weight of a randomly drawn bag that is made by me, and suppose X is following normal distribution with 2 and 0.1. That means in average, I can really produce bags of candies that weigh 2 kilograms, but there are some fluctuations. Okay, and the fluctuation here, the standard deviation is 0.1 kilograms. I probably do not know whether this is good or not. I can put more efforts on my job and to reduce the standard deviation. Okay, I know my mom will be happy if I can reduce the standard deviation because the quality is better controlled. But I don't want to put efforts. I'm just lazy. Okay, so I want to ask myself whether this 0.1 standard deviation is small enough. How may I do that? I need to ask what's the probability for my bags to be out of control. Okay, if my mom set this rule to me, I need to make sure that the probability for my products, for my bags, to violate its rule, the probability must be small enough. So I need to know that probability. Now, I set a bag to be following this normal distribution, right? So I know 2.2 kilogram is exactly 2 sigma above my mean. So this is going to help us answer the question in the previous slide, whether 2 sigma is far or close. Let's continue. So I know what I'm doing is that I have a normal distribution with mean. The mean is 2 and the standard deviation is 0.1. Then I am asking, what's the probability for me to violate my mom's rule? What's the probability that when she randomly take a bag, she will find the bag is very bad? Okay, she will find the weight is above 2.2 or below 1.8. Okay, I want to know what's the probabilities. And obviously this comes from two different probabilities. It's the probability for x to be too large or the probability for x to be too small. Graphically, it seems that the probability is not very large, but let's try to calculate it. So definitely we don't want to do any mathematics. So we will just call this R function. This P norm stands for probability of normal distribution. Okay, so how does that work? You need to tell the computer what's the mean and the standard deviation of your normal distribution. That's going to help the computer set up a normal curve. And then you give him a number q. The computer is going to tell you what's the probability for your x to be smaller than that particular number q. Okay, so all you need to do is to specify these three numbers. In our example, the probability for my bag to be bad is the following. I want to find the sum of these two probabilities, right? And I can do this first. Okay, do the second part first. The probability for x to be less than 1.8. So I know q should be set to be 1.8. And then I know I need to set up the mean and standard deviation. So that's this, 2 and 0.1. So that's probability of x less than or equal to 1.8. How about the other probability? No, it's something that is at the right tail. Okay, it's something that means x is greater than or equal to 2.2. Here, I don't really need to calculate it again because I know it must be identical to the probability for x to be less than 1.8. This is because this curve is symmetric, right? This curve is symmetric. So I can immediately see these two probabilities are the same. Suppose I want to calculate a somewhat different probability. Okay, let's say it's here. It's the probability for x to be above 2.1. Then what should I do? I simply need to calculate the probability for x to be below 1.9. In any case, if I want to calculate the probability for x to be greater than or equal to mu plus d, for a certain number d, all I need to do is to calculate the mirror image on the probability for x to be less than or equal to mu minus d. Okay, so anyway, I can use R and apply this observation to get my probability. And after this calculation, I can see, okay, there is a probability 5% that I am producing something that is out of control. So with probability 5%, my bag does not pass the quality standard set by my mom. It's either too heavy or too light. And then it depends on whether I am risky or not. If I am a risky guy, then I probably will take this risk. And I will say, okay, I will just still be lazy and I will not try to reduce my standard deviation. But if I think, or if my mom will give me a very large penalty when she finds I am not doing a good job, then I probably need to put some more efforts to lower my standard deviation. Okay? And then with my knowledge about probability, I can answer the following question. What's the largest standard deviation for me to reduce this probability to, let's say, 1%. Okay, I can answer some questions like this so that I can do a better quality control problem. In general, as long as your distribution is normal, then we have these following general guidelines. For any normal distribution, the probability for the value to occur within one standard deviation is around 60%, 68%. So I am saying for this particular region, the probability or the area is 0.68. Okay, if I set a higher quality standard to 2 sigma, then I'm going to get something that is 95%. Okay, that means with probability 95%, my outcome will be within 2 sigma from the mean. Or if I am saying 3 sigma, then it will become very close to 100%. So think about the situation that you are the manager of a factory and you are producing a product and you are having the similar quality control problems. Okay, your task is to decide a quality standard. If you set your standard to be, let's say, 1 sigma, then you will have an yield rate that is 68%. If you increase your quality standard, then your yield rate will become larger and larger. And if you insist that all your products should be within 6 sigma from the mean, then your yield rate will be very large. Okay, so probably some of you have heard about this term 6 sigma in the past, and that basically means all my products should be basically perfect. Okay, about quality management. The last thing to tell you before we close this section is the term cumulative distribution functions. As you will see, it's so often for us to calculate the probability for a random variable to be smaller than a given value, just as what we did regarding this quality control example. Okay, and especially for normal distribution, if you want to calculate something that is above a threshold, we can always do that by calculating its mirror image. So we specifically define something called the cumulative distribution functions. Okay, we call it a CDF and typically expressed as the capital F function. We define this cumulative distribution function as the probability for x to be below that value. Okay, so naturally with the previous example, f of 1.8 would be around 5%, and f of 2.2, okay, should be probability for x to be less than or equal to 2.2 by definition, right? And it's 1 minus the probability for x to be above 2.2. And we know what's this. This is 5%, right? This is this particular area. So that's why the probability for x to be less than 2.2. Oh, it's the area here. Okay, everything up to 2.2 will be 95%. Okay, so now you have an idea about normal distribution, something like a bell. Okay, symmetric, central tendency. You know there are mean, you have standard deviation, and you know sometimes we want to calculate a cumulative probability, and we may have cumulative distribution functions for doing that. In the lectures, we will give you some exercises and some demonstrations to give you more ideas about continuous and discrete distributions. And then starting from the next week, we will start to use them to do statistical inference. Thank you.